This is definitely the thrill of a lifetime. Little did I imagine when we started building Keck back in 1977. That was the first meeting at Santa Cruz in which the thought was expressed that we could begin to think about going beyond the Palomar 200-inch. Little did I think back then that some 35 years later, I'd be standing here reviewing the first 20 successful years of this wonderful telescope. And it's particularly wonderful for me because I got involved with the goal of really wanting to look back in time. I thought that was such an amazing thing, that a telescope could take you back in time. And again, little did I realize that we would be looking with Keck to within 400 million years of the Big Bang itself. So my theme here is a little bit different from the speakers that you've heard up to now, who I think collectively have been emphasizing the exploratory nature and the wonderful new things that Keck has discovered. My approach in this talk is going to be to emphasize actual hard knowledge that we have discovered and solidified with Keck. And there's an analogy here. I think in galaxy research, we're sort of where we were in stars in the 1930s and 40s. You'll recall that that was the era in which it was realized that stars were powered with nuclear reactions. And that was the key breakthrough that made their formation and evolution understandable. In exactly the same way, we've made breakthroughs with galaxies, and we now can classify them. We see a family there, and we even have a theory which accounts in broad outline for their properties. And that's what I want to talk to you about, because so much of this, the evidence in favor of this, has come from Keck. Now, let's start by showing one of the most remarkable movies, I think, that has been made in astronomy by Brent Tully at the University of Hawaii. The purpose of my showing you this movie, which starts with a fly towards Orion, is to give you a mental landscape of what it is that we're actually trying to explain when we develop a theory for galaxy formation. So the beginning of this movie is a fly towards Orion, through the Orion Nebula where stars are forming, the Horsehead Nebula, and you get a sense of our galaxy, a great stellar city in space, 100 billion stars, permeated, suffused with interstellar matter. Those are those dark dust clouds that you see there. Here we're coming to another star-forming region, the Rosette Nebula. These regions light up because their ultraviolet light excites surrounding gas and causes it to glow. We call those emission line regions, or H2 regions. And here's another H2 region, but this time it's a dying star. This is the Crab Nebula, which exploded about 1,000 years ago. And now, in what is truly a remarkable section of video, we fly out of our galaxy, and this scene is magically made to morph into a nearby galaxy, a real one, which we think looks very much like our Milky Way, a barred spiral. So this is an actual image of a real galaxy, seamless transition. And you can see the large Magellanic Cloud, the small Magellanic Cloud. We're flying out into space, beginning to probe the region of our local group of galaxies. The view pans around, and we take a look at the great Andromeda Galaxy and its neighbor Triangulum, M33. We're going to fly through M33 with its huge H2 region here, a region of intense star formation. And now the camera pans away out of the local group to look at galaxies in our region of space. And this is what is really remarkable about this movie. Only Brent could have made this movie because he has made a career of mapping nearby galaxies. Every image that you see here is a real object. And it's placed at the right distance, and it has the right size. So the only thing that's fake about this movie is that everything is brighter than it would seem to your eye. You would need telescopes to make things look this bright. but the placement of objects, their distribution in space, and their relative sizes is realistic. And so what you can now see in this movie is that there's structure in the form of galaxies, and the galaxies are not uniformly distributed. They're distributed in small clumps and filaments, and where the filaments intersect, we get gigantic clusters of galaxies, and the nearest example is this one, the Virgo cluster. And at the center of these clusters, you often have these truly humongous galaxies, behemoths. This is M87, and we stop there, which is a good thing because M87 has one of the largest known black holes, 10 to the 10th solar masses at its center, just as well that we don't go any further. Okay, so in trying to explain galaxies, this is what we are trying to understand. And you can already see that from this movie that there are some rules about galaxies that are visible today. The rules at today's era are that galaxies have a typical size and mass, which is something like 10 to the 12th solar masses. And you will have already seen that there are two basic morphologies. There are these rotating disks, and then there are these gigantic, humongous galaxies that are more spherical, disks and spheroids. And that the galaxies are distributed irregularly in filaments, groups, and clusters. And you're intrigued by that idea because the thought occurs to you that maybe you could do some statistics on that distribution and in that way understand where it comes from. Okay, so it turns out that we have a wonderful theory that explains virtually everything that we just saw in the previous slide. It's called the Lambda CDM theory of galaxy formation. And Lambda CDM is a name which describes what the universe is made of. CDM is cold dark matter, and that turns out to be really crucial to this theory. And lambda is a label that indicates that there's dark energy in this universe. And dark energy is inimical to galaxy formation. It's a repulsive force. So fortunately, there's not too much lambda in our universe. And as far as the theory and models go, we can almost ignore it completely because it wasn't very important early. And cold dark matter, matter in general, was doing all the work for us. So for our purposes today, we just might as well call it the CDM theory and forget the lambda. So let me sketch to you the basic ideas about this theory. It starts with the fact that very early on in the universe was almost uniform. It's very lumpy today. We saw that in the picture. But early on, it was very smooth. In fact, there were density fluctuations about 1 part in 100,000. And that's all it took. Because where there's a density peak, matter is drawn in as the universe expands. Where there's a valley, matter flows away from that and onto neighboring peaks. That's gravitational clustering. That is why the galaxies are there. And it's an instability. It's a runaway instability. And we have a perfect analogy in real life. It's called the rich get richer and the poor get poorer. So galaxy formation is actually economics on the grandest imaginable scale. So this is a picture of the universe at the earliest time we think we can really talk about this process, which is at 10 to the minus 35 seconds at a temperature of 10 to the 27th degrees. This is the period of inflation when the universe was actually expanding bigger than the speed of light. And that is critical because it's that expansion that imprinted the fluctuations, 1 part in 100,000, that caused the galaxies to grow. If I have time, I'll come back and talk about the fluctuations at the end. But in the meantime, I'd like to move on and call your attention to models of this clustering process. And we saw this, a little bit of this film yesterday. Let me just show it briefly. Okay. Right. So this is cold dark matter clustering from the initial density fluctuations, and it's making a galaxy that looks like the Milky Way. Well, that's fine, but that's not what we actually see, as Marla emphasized. Dark matter is well named, it's invisible. And so in order to figure out what we see with our telescopes, we have to put in ordinary matter, which astronomers for some strange reason call baryonic. And this is another remarkable video. It's not shown enough by astronomers. This was made by a bunch of Japanese. And I don't even think it's on the web anymore. I'm not sure you can get a copy. This is the same process, clustering driven by the dark matter. The dark matter is invisible here. And this is the ordinary matter, hydrogen and helium coming out of the Big Bang, condensing in the potential wells that are formed by the dark matter to make visible galaxies. And you'll note that as the matter falls into those potential wells, it has some spin, like water falling into a drain. It never goes exactly in. And that spinning motion causes the matter as it falls in to settle into rotating disks. And so this is our first hint that rotating disks are a very natural structure to expect for galaxies as they're forming. Now, you will have noted that at the beginning of this process, it's very chaotic. The universe is full of lots of lumps. They're close together, they collide, they disrupt one another. And every time they collide, the stars that had been made up to that point get thrown into a halo around the galaxy. We call that a spheroid. That's the formation of the spheroid process. And then any leftover gas that's still falling in settles to reform the disk. So we think that early galaxy formation is a repetition of this process of disk formation, merger, disruption, spheroid formation, and then settling down until the next merger. So this video here makes us think that there should be two great morphologies among galaxies. One is the rotating disk, and the other is the stellar spheroid. And in general, the stellar spheroid will be older because it consists of the stars that were made before. Well, we're delighted to look at the structure of local galaxies and find out that this is true. Galaxies exhibit both disks and spheroids, just like this model predicts. Here are some objects that are mostly disks, like our Milky Way, and here are some objects that have mostly spheroidal morphology. So that's reassuring, that's comforting. But we need more in order to verify this theory. What we really want to do, the power of this theory is that it predicts things as a function of time. So what we really want to do is go back in time and see if the evolution of structure is as predicted. So enter telescopes. Let's start with the Hubble Telescope, and its deepest picture to date is in the ultra-deep field. And let me tip a hat today to Steve Beckwith, who's sitting in the back row, who is the person who helped Hubble organize the ultra-deep field when he was the director. Here's the size of the ultra-deep field shown to scale on the moon. So you're getting the notion that the ultra-deep field is not that large. It's about 1/10 the size of the moon. And here is what the whole picture looks like. There are about 10,000 galaxies here. It's a completely typical region of sky. And if we blow it up, the miracle of Hubble shows us all the detail. You can see that potentially there are a lot of things structurally that you could measure in this image. It's very rich. Now you can do even more. You can at least roughly estimate how far the galaxies are away. And hence, in another remarkable movie, the makers of this movie have strung the galaxies out in space, mimicking what we would see if we could fly out in space along the Hubble Deep Field. But keep in mind that as we do that, we're also flying back in time. So this is a flight through the galaxies, out in space, and back in time. This is what I always wanted to do in building the Keck telescope. So the goal here now is to study galaxy evolution. We're looking at it sort of backwards, going back in time here. My movie seems to have stuck there for a moment. And the point I wish to make is that these early galaxies, which are near the limit of Hubble's sensitivity, are different. They're smaller, they're ragged, they're more irregular, and you will already have known from looking at that movie that this is exactly what we expect. So now, what's wrong with this movie, or what's missing? What's missing is really accurate distances. And to get really accurate distances, we have to take spectra, at least of some of the galaxies in this field. And that was my project to build the DEIMOS spectrograph and conduct the Deep 2 survey with the Keck telescope. So DEIMOS is a very large object, weighs 20,000 pounds, takes a lot of spectra at one time. It's interesting getting these instruments to the telescope. There's DEIMOS in a little shipping container there. And here's its home on Keck 2. This is what it was like getting it through the slit. Here's the crew taking our picture. We're about to go down in the next 15 minutes. We took the first spectrum. And just like MOSFIRE, DEIMOS worked right out of the box. And this is a bit sobering. This big spectrograph, which seemed so huge, you now see it on the telescope and it looks kind of tiny. Now, DEIMOS takes 140 spectra at a time. That's important. That's like building 140 Keck telescopes. This multiplexing is a huge advantage. Let's take a little piece of this exposure and blow it up. And now you see several spectra shown much enlarged, a short segment. This is the blue end, this is the red end. And there seems to be a lot of nice stuff in this spectra, but unfortunately most of it is garbage. All of these vertical bright lines are produced by our Earth's atmosphere. You have to get rid of them. And so there's a post-processing art which removes them, and when you do that, voila, look at all these features that emerge. Those are the galaxy spectra. So we can measure many things from galaxy spectra like this. First of all, from the basic shift of the features, the redshift, we get the distance. From the brightness of these emission lines, we can estimate the star formation rate. From the width, the broadening of those lines, using the Doppler effect, we can estimate the internal orbital speed of the gas in the galaxies. And from line ratios, oxygen versus nitrogen versus hydrogen and so on, we can estimate the composition of the gas in these galaxies. So using this information, we conducted the deep survey, which looks about 2/3 of the way back to the Big Bang. Here's 7 million years. We also went out as far as 9 million years. So we, in this survey, are looking sort of at preteen galaxies. They're not babies. You're going to hear about the babies in the next talks. But on the other hand, they're not fully formed either. So it's possible to make a nice link between galaxies today, which are mature, and the preteen galaxies that we see there, and understand the processes that are responsible for their evolution. So just to get you calibrated, this is about where the Sun and Earth formed. So the high point of the Deep 2 survey gets us to see galaxies before our own Sun and planets formed. In other words, they're showing us what our Milky Way was like before the Sun formed in it. Now, a very important point is that as a result of the Keck observations and other observations, we have discovered rules about galaxies called scaling laws. And here's an example. This is a plot of stellar mass on one axis and log of the internal orbital speed. So this is galaxy size this way, and this is how fast the stars are moving. And you can see that there's a rather nice relationship. We can develop a rule which says that stars orbit faster in bigger galaxies. The next plot was shown by Chuck Steidel in his talk, and it was developed by his group. This is a plot of gas composition called metallicity versus stellar mass. That's oxygen abundance, and again, stellar mass. And you can see a trend. Bigger galaxies have more heavy elements. Now, the interesting thing about this plot is that there are 2 times shown. The lower set of points are earlier galaxies, and the upper set of points are galaxies today. So not only do we have a scaling law in this case, but its 0 point is changing. It's drifting as a function of time. This makes perfect sense because we know that these heavy elements come from star formations, from supernovae and other stars that are cooking these elements. The original galaxy was pristine, had only hydrogen and helium, and over time, these elements are becoming more abundant. So actually now that makes us think and reflect. Probably these objects here have very few planets. Because as many speakers have now been telling you, it seems as though we get going in planet formation by forming these rocky cores, and that requires a lot of heavy elements. So maybe galaxies down here at early times don't make planets. In fact, maybe our sun was one of the very first stars in the solar neighborhood that was metal rich enough to make planets. An interesting thought. Okay, star formation rate versus stellar mass. That's my next scaling law. Again, this is relative star formation rate and stellar mass on that axis. And you see different colors here. Each color is a different epoch in time. So pick an epoch, looking back in time, look at the green points. What this graph says is that the bigger galaxies make stars, in a relative sense, less actively than littler galaxies. So there's a rule there, another scaling law. Bigger galaxies make relatively fewer stars, or make them more slowly. So I've now given you examples of scaling laws, and let me remind you how important a scaling law is for gaining insight about a process. And I'll use as an example the HR diagram, which is a scaling law for stars. It plots luminosity on the vertical axis versus surface temperature. And there are a lot of other scaling laws that we could plot for stars. That was the key, the discovery of that plot. Stars are not just anywhere in that diagram, they're on a line. That was the clue that told us that we had to understand nuclear reactions in stars. In exactly the same way, in a way that I really won't have time to discuss in detail, the existence of these scaling laws and their zero-point evolution with time is a clue that there's a theory out there about galaxy formation and we need to discover what it is. And the good news here is that, in fact, the Lambda CDM theory is exactly what we need to explain most of this. So if there's a takeaway message here, the message is that first and foremost, galaxies are a sequence in galaxy mass. So we have at the massive end these very large spheroidal galaxies, and we go through a series of disk galaxies forming stars more actively until we get to ragged, irregular galaxies. They're small at the bottom end. So this could be summed up by saying big, middling to small. And you say, well, they don't really look like they're changing in size. That's because I wanted you to see what they look like. If I actually plot them to scale, that's what the picture would look like. See, so big here, down here, there's about a range of about 1,000 in mass between the two ends of the sequence. So let's return to our thoughts at the beginning. Is it possible that with this Lambda CDM theory, we can explain this sequence? And the answer is yes, we can. The key element is the dark matter halos, which affect the star formation and many other properties of the galaxies, and wind up imprinting a mass sequence on galaxies that we see today. So all of it that we see today stems from this near uniform but not quite uniform density fluctuation early on at 10 to the minus 35 seconds, 10 to the 27 degrees Kelvin. What's going on there? What's going on is inflation. I told you about that. Inflation generates Hawking radiation. An inflating universe is like a black hole inside out. Black holes collapse at faster than the speed of light inward. An inflating universe expands at faster than the speed of light outward. Both of those phenomena generate quantum fluctuations and radiation. They produce radiation which produces density fluctuations in the universe. So we could imagine flying through the early universe and having a little meter that measures the density from place to place. And here's a part in 100,000. That's what we would see. And around one of these peaks, blowing it up, this area here is going to nucleate a galaxy. How does the mass of galaxies today relate to the peaks that we see here? A more massive galaxy it was lucky, it started from a bigger peak. So the size of the fluctuations originally in the early universe at this early time imprint themselves on the mass and properties of galaxies today. That's what the theory says. So I think, what have we said here? We have said that by sitting here on planet Earth, looking at galaxies around us and back in time with giant telescopes like Keck, we have actually managed to probe the evolution of the universe back to 10 to the minus 35 seconds. And we have discovered that our Milky Way, which is 100,000 light years across today, is the child of a quantum fluctuation which was once 10 to the minus 33 centimeters in size, that got captured by the expansion of the universe. It wasn't allowed to die away. It got seized by the throat. It got frozen in. Its gravity produced the galaxy that we see today. We're all children of quantum mechanics. So I'll leave you with that thought. I never realized, as I was a graduate student wondering about galaxies, that I'd be able to stand here today and tell you this story. Thank you.